is Sarah and I'm the project manager of the Phoenix UAV project. I'm just going to give you a brief introduction to the problem that this project is aiming to solve. Jaden, our lead systems engineer, will take you through the Phoenix UAV project. And then we have Amy, Katarina, and Sinead who will take you through the design concept which our team has come up with. Now, Australia is a vast dry bushland which suffers from severe and frequent bushfires. Unfortunately, these bushfires threaten Australian livelihoods as well as, more critically, Australian lives. To be able to effectively mitigate against these bushfires, Australian firefighting services need to have accurate and up-to-date maps of bushfire fronts as well as bushfire extents. The current technique to undertake this bushfire surveillance is to use a manned plane which flies over bushfires and sends back the data which it captures to a nearby headquarters. Unfortunately, in October of 2013, a bushfire pilot was killed undertaking this bushfire surveillance. So we would like to reduce this risk. Another strategy which is used to survey bushfire areas is to use a satellite. Unfortunately, this suffers from limited coverage as well as limited resolution. I'll now pass over to Jaden, who will tell you more about the Phoenix UAV project.
Thanks, Sarah. So Team Phoenix is attempting to address the problem of monitoring and surveying bushfire fire fronts in any bushfire-prone region of Australia, utilising an unmanned vehicle. So to do this, we're exploring the concept of using a UAV. We'll be exploring multiple different concepts throughout the course of this presentation. The UAV must be able to take infrared photos of the fire front with an accurate timestamp as well as GPS location stamp, accurate to within 100 square meters, and with a minimum flight distance of 5 kilometers away from a mobile ground station. So the UAV will take these infrared images and then, as a requirement, send the images back to the ground station manned by the State Emergency Services or Royal Fire Service. And these images will have a 1 minute maximum latency. From these images, the firefighting services should have a better idea of where the fire fronts are located and should be more effectively able to combat them. As a requirement, we would like the UAV to have a 30-minute time of flight. This is purely so that it can perform multiple sweeps of the fire front. And in addition, the UAV must be able to be remotely controlled by a single personnel, and this will be done from a mobile ground station, as previously stated, via remote control. The UAV will have a forward-facing camera on it, which will provide real-time images back to the ground station so that the pilot can see where they are steering the UAV. Finally, the UAV must be upgradable and maintainable so that it can achieve at least a 5-year lifespan of operational service, and in addition, so that if new technologies were to arise, that the UAV could be upgraded and installed with these new technologies. I will now pass over to Amy, who will go over our first consideration, which will be looking at a fixed wing UAV versus a rotary wing UAV.
Thanks, Jaden. Okay, so as Jaden just told you, we'll be doing a quick analysis of the differences between fixed wing and rotary wing UAVs. So firstly, the main difference between these two different types of UAVs is that fixed wing UAVs have wings that are obviously fixed in a certain position, much like a conventional aeroplane. Due to the way in which the wings are designed, lift is produced by forward movement and rudders are used for steering. A rotary wing UAV, on the other hand, produces lift by using rotor blades that rotate around the mast, and steering is facilitated by changing the relative speed of these rotors. The most typical type of rotary wing UAV is a helicopter, but UAVs tend to use 4 rotors, and these are known as quad rotor UAVs. Takeoff and landing is more complex in fixed wing UAVs since they need quite a bit of space. There are different methods of takeoff and landing, such as hand and catapult launch and parachute landing. Rotary UAVs are more versatile in that they can take off and land on any level surface without a lot of space. Fixed wing UAVs can carry a greater payload, are faster, and can fly for longer than rotary wing with the same power consumption. However, rotary wing UAVs have the unique capability to hover and fly close to targets. Since our UAV is for providing up-to-date surveillance information of bushfire-affected areas, maximising the speed, range and height is desired. In addition, since the UAV must be capable of carrying surveillance equipment, we require a UAV that can handle a relatively heavy payload. For these reasons, the Phoenix team recommends the use of a fixed-wing UAV for this project. I'll now pass on to Katarina, who will be going through the different options for powering our UAV.
Thank you, Amy. We've considered three main options for powering the UAV: petrol fuel, lithium polymer batteries, or a fuel cell. The advantages of petrol fuel are the high power density. It's easy to acquire and it's relatively inexpensive. The disadvantages are that you would need much more vibration isolation for the engine, and obviously if you have a petrol engine flying over a bushfire and the UAV crashes, there's a risk to the recovery of the vehicle and any data that it has stored. Also, it would not be optimal to use a petrol engine in a rotary wing UAV because it couldn't provide the immediate changes in voltage that it would require for manoeuvring. The benefits of lithium polymer batteries are that they are solid, sturdy, and no data would be damaged if the UAV crashed. They're rechargeable, they have a fast rate of recharge, fewer parts are required. For example, you don't need an alternator. The drawbacks are the power capacity eventually drops with charging and recharging, and that the low power density means that the battery is relatively heavy, but you get quite a short flight time. A fuel cell would give the longest flight time, and it's much more efficient than petrol. Unlike batteries, the reactions do not degrade the fuel cell over time. But the disadvantages are the high cost. Most types of fuel cell have quite high operating temperatures. And the most important thing, fuel cells use hydrogen or hydrocarbons or alcohol, which are quite flammable. So it's the same problem as with the petrol engine, where if it crashes, you'll lose the vehicle and probably the data. We recommend lithium polymer batteries because they are relatively easily available, fairly low cost, and the system would be modular and require fewer parts and thus be easier to maintain. Now we have Sinead, who will talk about whether to have a single UAV or a swarm of UAVs.
Thanks, Katarina. So, for our system, we have two options in terms of scale. We can have a single aerial vehicle, or we can have multiple aerial vehicles working in coordination. So first I'm going to go through the advantages of a single UAV approach. Managing the maintenance of the system is quite easy because we only have a single vehicle and then the ground station. Monitoring is also easy because we only need a single pilot and possibly one SES personnel to analyse the data that's actually coming in. Designing the system is simple because we don't need to worry about coordination of multiple vehicles and we don't have multiple communication links. We can also focus our resources onto producing a high performance vehicle instead of producing many vehicles with average performance. At present, there is a lot of open source development in single UAV systems, so this means there will be an accelerated development time. The disadvantage of this approach is that it's not very scalable. So if we want to survey a larger area, it's obviously going to take a longer time due to the speed constraints of the vehicle. There's also no redundancy in this system. So if the UAV goes down for whatever reason, we don't really have any other backup UAVs to do the surveying process. So now I'm going to go through the advantages of a swarm approach. With the swarm approach, we have multiple vehicles going out and doing the survey, which which means we have a higher data return rate, and we can get a more rapid overview of the extent of the fire region. There's also inherent redundancy in this system, so if one UAV goes down, we still have several others in place to continue the survey operations. It's also more scalable. If we have a larger area to survey, we can easily send out more UAVs and get the same response time as if we were surveying a small area with a single UAV. The SES may require us to monitor multiple fire fronts at the same time, and again, this is possible if we have multiple UAVs. It's also possible for us to have continuous flight time by using a staggered recharging approach. So we can send out all the UAVs at once, and then at regular intervals, we can bring back certain UAVs for recharging. We can also put different sensors on each UAV, so depending on what information we require from a particular area, we can choose the UAV suitable for that and send it off. With a single UAV, we wouldn't really be able to do this because we can't pack on a lot of different sensors onto a single platform, as there are weight restrictions, and this would have reduced efficiency. The disadvantages of the swarm approach is that the ground station is going to require a higher performance. It has to handle a lot of incoming data and also do real-time control for each individual vehicle. There will be an increased maintenance cost because there are more vehicles and the equipment is more complex. And usability is decreased because we'll need pilots to monitor each of those vehicles. We also have to think about how we're going to be transporting this system to the region of operation. As we have a lot of equipment, it's going to be a lot harder to transport it as well as store it in the meantime. It is more expensive to run this system because there are more vehicles and they're all consuming power. Launching and landing of each vehicle is complicated because we have to consider the case where we might want to land multiple vehicles at the same time. So that might mean that we'll have multiple nets to catch these vehicles, or we might have backup systems such as parachutes. Reproducing this system will take more time and effort, and at present there is limited available research in the area of multi-UAV swarms. So this means that developing this system will take longer. So based on this comparison, we recommend that a single UAV system is implemented. So this is due to the rapid development time, low maintenance, low cost, good usability, and low risk of this technology. So now I'll pass over to Jaden to finish the presentation.
Thank you, Shannon. So given the considerations of the Phoenix team, the Phoenix team would like to recommend a fixed wing, lithium polymer powered single UAV system. After preliminary investigation of existing technologies, it has been found that a UAV in the magnitude of a 12-foot wingspan UAV flying within the castle regulation at 133 meters in the air, utilizing an infrared camera with a field of view of 90 degrees, which is fairly moderate, maintaining its altitude via LiDAR, traveling at a modest 80 kilometers per hour. Once it gains altitude, would be capable of performing a sweep of a 250 meter by 5 kilometer fire front in 3 minutes 45 seconds. Given the requirement of being able to send information back with up to a 5 kilometer distance from the ground station of 1 minute, this would mean that within 5 minutes of gaining altitude, the UAV would be able to send back a complete sweep information of the fire front. Within 30 minutes, the UAV would be able to perform up to 8 sweeps of the fire front before having to land. Now, I'd like to ask Sarah to join me if you have any questions.
From my point of view, the fixed wing is the right approach, but you've got practical issues taking off and landing. How many metres wide did you say?
We're looking at
3 metres.
We've investigated a couple of different landing
Well, I think partly it depends on what sort of terrain you're going to be dealing with. You can take the view that if you're in mountainous terrain, they probably don't care that much anyway. But a lot of damage is done out in the open fields, like down in Victoria, where it's grass fire mainly, a bit of bush, predominantly flat land with occasional hills. I think that's what you're trying to protect more than anything. So the fixed wing approach is probably, in my view, the optimal. The power to weight ratio is a lot better than having the four engines of the hovercraft in the more power. It's much more complicated. So intuitively, I think that's the right approach. I also took the view, and you might have seen it in the emails I sent out, that it has to be capable of flying completely blind. Solely by reference to positional data from the GPS and probably map data that I don't think would be too difficult to organise. I presume that's where a bit of research is going in.
Absolutely.
Yeah, but it'd be good to build on that. You also got to remember that some of these fires travel very quickly, in excess of 30 kilometres an hour. So, did you actually think whereabouts the control stations would be relative to a fire front? Would they be behind? I think that's where I'd prefer to be.
Absolutely.
Yeah.
Sorry, just to answer a few of your questions.
Yeah.
So, in terms of maintaining its altitude, we're looking at using an altimeter in conjunction with a LiDAR to so it can maintain altitude above
You can get it off GPS, you know.
So what's the rationale behind LiDAR? Like, that seems like an interesting design choice, but why LiDAR in particular?
Was Joey? Did you want to talk about LiDAR?
Did you? So the question is, who here worked on LiDAR for the?
You mean the communication transceiver?
No, talking about altitude.
I think that was just, I do not think that LiDAR systems are very expensive, so it just built in a bit of extra redundancy, even though we could use the GPS coordinates.
Yeah,
Having a LiDAR would allow us to more accurately.
What's a LiDAR?
light radar basically. So it's radar.
Oh, okay.
Just sends down to the ground.
Yeah, because I was instantly going to refrain from the barometric altimeter approach.
Yeah, so if you can get this information without adding weight, so if you add a LiDAR system to it for measuring altitude, you need to weigh up, how well do you need to know your altitude? I mean, LiDAR is a very accurate device, but is it absolutely necessary? Because you're going to bolt on something that might weigh half a kilo. And for your UAV, every kilo adds to the wingspan. It's a very non-linear effect. Everything gets more complicated. So, is it necessary, or what can you simply load in basically a map, like a Google map that tells you what the terrain is and has contours on it, so that you know where your base station is, and based on the GPS coordinate, which is going to have X, Y, Z, and Z being, I guess, altitude.
Velocity.
Well, you're going to have velocity as well.
You got to have, with that, you're going to have velocity factored in because you're essentially terrain following.
Yeah.
So you're definitely into a real-time environment with predictability involved, because you've got to know who you are now and where you're going to be X number of time down the track. The beauty of the hover approach is, well, if you get confused, you can sort of stop. As a pilot, I can tell you that you don't have that luxury in one of those, and I don't think the computations required are onerous either. You can get some lightweight computing power that can take all of the sensory input, basically your GPS inputs. That's giving you velocity as well, but there is a bit of a lag with velocity. So if you're turning, you have a little bit of a lag before you get your new velocities. But over relatively flat terrain, I think this would work very well, especially where they want it, because they're trying to predict, not so much, well, they want to know where this thing's going and when. They need velocity of the fire front more than anything. They need to be able to do it safely. I think the market would be in that area. Sure, we want to keep the fires out of the hilly, the national parks, but practically I don't think well, knowing where they are is one thing. Doing something about it is another. You can't get the fire trucks in there anyway. We don't have the resources to have the big aircraft they have in North America to go and fly down a valley and drop 20 tonnes of water or fire retardant. We just don't have that. We have the helicopters, and what we're trying to do is supplement them, I suppose.
Well, it's strategy. It's where so at the moment they go and dump water and fire retardant in particular areas, but if you can locate, where a fire front is pushing forward, then you can be very strategic with where you're actually dumping water, and that's the kind of information you want to provide in the service.
Yeah. Another factor you've got to consider is around these fire fronts, you can get some enormous wind velocities. Yeah. And this thing, you're talking about a 45 knot airspeed. You could have that going backwards in a fire front, so you need to consider your options there as well.
Actually, that's a good point. Just really quickly, I know that you discussed this, at least Zach was considering it, but the concept for surveillance, are you going with a downwards facing IR camera, or are you going to have a forward facing IR camera and then infer the location of the fire front based on your knowledge of its pitch and field of view? Which one are you going to go for?
So we were looking at it downward facing, and with regards to your location and placement of the ground station and where we launch it from. So just off what you said, so if we place the ground station behind the fire front, it's assumed that the fire front would most likely be moving with the direction of the wind. And so at least what that would mean is that once we launch the plane, it could get over the fire, and then it would most likely have to fly at some kind of angle to,
Or just keep going somewhere. It means you've got two locations you need to operate from.
So I have this problem, which is thermal. Right, so you're going to have a huge amount of hot air rising from this fire, okay, so you're going to have a lot of thermal activity, right, which is pushing air up.
I'm not quite sure what the effects of these high intensity fires are on radio, to be quite honest. When you've got these high temperatures floating around, especially with flame, I'm not sure if there's any effect on. There's a lot of heat, I know that.
I wonder if that would actually. That's an interesting thing to look at. That you should probably.
Yeah, I don't think.
I don't even thought of it because it's the energy.
And has anyone looked into what the levels of oxygen are likely to be in a fire front where this thing's likely to go? That could force your issue towards the battery away from a fuel driven. Because I know people have suffocated as fires come up a hill. They've jumped in the swimming pool and they're suffocating because the fire is just sucking all the oxygen out. There just isn't enough to.
And that's a really good point as well, because if there's smoke, so if the UAV is engulfed in smoke, obviously there's going to be low level oxygen, and so a combustion engine.
Yeah, it has absolutely has to be able to fly in zero visibility conditions.
Which is the reason that was a big design consideration when we decided to use an IR camera, infrared camera, over a conventional lens. So
we
definitely
see. There's another issue as well that I just thought of. By going to the fixed wing approach, you absolutely need to know your airspeed. The GPS system can give you essentially your ground speed, but your airspeed is something completely different again. So you'll need a little a pedostatic or some sort of device that tells you what your airspeed is.
Andrew, is that part of your guys or?
Yes. Yes, so airspeed differentiation, not something we had considered. We had looked at just going back a step, we had looked at the plume in terms of the oxygen content, which is why this is one major consideration for the battery approach. So yeah.
Well, airspeed is the essence of flight, and if you're this thing's got a 45 knot capability, and all of a sudden it makes a turn and finds itself with a 20 knot tailwind that's going down. That's it, it's going down. So it needs to know, so it knows what to do about it. It's like a little autopilot. It doesn't need to know its altitude so much, but it certainly needs to know what the airspeed is. And there's only one way to do that, and that is to have a little tube poking out the front with a simple airspeed. Even the most sophisticated jets use it.
Like a barometer style.
Yeah, it's exactly what it is. And of course, if you haven't got the oxygen there, that could be interesting as well, because fortunately in Australia we're all pretty low altitude, but the way these things work is a function of air density. And yeah, and you don't have a lot of margin for error here. You're talking about a cruising speed of 45 knots. Probably at 35 knots, you're not flying anymore.
Yeah.
So I can see all sorts of issues, but I believe even with the technology that's currently available, it can be overcome without a massive amount of expense.
Yeah, it doesn't sound like it should be too much. I mean, I'm presuming you're going to be looking at commercially available UAVs, fixed-wing UAVs, that have payload capabilities. So one way to simplify this immensely is to look at, I know that you can do this in the United States at least, is look for a basically pre-made UAV that has a payload mass capacity, right? It can take up to 3 kilos of payload or extra stuff.
It can be transported as well.
Yeah, so that's another question is,
Can it fold?
yeah, can you fold it up?
Yeah, can you take the wings off and things?
So,
Yeah, whether you have to, do you have to pull everything out of the tray of your truck or whatever and bolt it all together, and how long is it going to take, or will it fold out? So if you have all this folding mechanisms, that's going to add weight.
Yeah, so these are things that, so actually for the transportability, so it's 12-foot wingspan. Okay, so probably half as long. So
See, the model aircraft enthusiasts will have all of this sorted out.
Well, we actually found quite a good model from F-38, and so that does fundamentally what we want to do. So that's capable, but that's only capable of monitoring at 2 kilometre radius, and like 2 kilometres squared, sorry. And also, it's obviously not designed for firefronts. It's designed for looking at like a farm trolley or something like that.
Yeah.
And it's a great system. And so we have been looking at existing technologies, and by making some pretty simple modifications, we reckon we can definitely.
well, the range. What's the range limited by? You say that's only got a 2 kilometre range. Is that what you're saying? 2 kilometre range from the ground station?
No, that's actually its monitoring distance, and so it can. They claim that it can cover with its camera taking photos.
Yep.
It can, after it's done its flight, it's returned 2 square kilometres worth of data, and they have a long range model, which is a lot bigger, where they claim it can do up to 16 kilometres squared. However, we're yet to fully explore that option, but it seems a little bit too good to be true, to be honest.
Yeah, well, if you limit your field of view to say 100 metres, that's an awful lot of linear distance in 16 square kilometres.
Is that what was the field of view? Sorry, of the sensor.
On the ones they used, they actually had a camera mount, and it was a Canon PowerShot 100. Yeah, it was just like a standard digicam, and so they had quite a broad field of view. I think it was 135 degrees.
It would have just a big lens on a fish eye.
Yeah, exactly. But infrared cameras generally they tend to range between 35 degrees up to 90 degrees, and the one we looked at had a 90 degree field of view. So
So when are you going to build this thing?
We'd love to. Well, this isn't even. This is just conceptual design.
Yeah.
So on a project-related note, this is good because I think maybe you've refined this interaction here with Jeff will allow you to refine your requirements somewhat for the final design, which is ultimately the best possible thing to happen to you guys. And just a note from a course point of view, this is why this should be held before your STS, right? This kind of thing, because you can really nut out a lot of the finer details, right? And so what I'm going to encourage you to do is basically go through the requirements you've currently got, and I know you've done up quite a lot of specs for them, but just have a look, see if you can, because a lot of the attributes won't change. The only thing that's going to change is the actual fundamental requirement of the system, okay? And you might want to go back and
I was talking before, you need 45 knots of you need airspeed to be, 45 knots going over the wings. And then you turn into a tailwind situation, you need the power for you to accelerate that mass to a point where you are at least 10 knots in front of it. So for example, you're heading into a 20 knot wind with a 45 knot ground speed. So you've got 25 knots up your sleeve and then do a 180, you've suddenly lost double the difference. And you've got to be able to accelerate that mass, get that double the difference back before you've flown out of the sky into the ground. So your power capability becomes a factor there. But again, not insurmountable. The beauty of the hovercraft, and that's why everybody's using it, is because you are able to have 4 counter-rotating blades with, so you can control your azimuth, what we call the azimuth position, which is that way, and with a combination of power applied to the 4 quadrants, you can control very easily your attitude. But that comes at a price, and I noticed that Amazon contemplating using them for deliveries. The next thing you know, your groceries delivered by a hovercraft.
It's a tough, but how we were talking about, I mean, that's a really good point, right? Is now you have before this CDR, you had some idea of what kind of power requirement you had, right? You had some notion of what was required to make this thing fly, right? Because one of your performance requirements is that, one of your functional requirements is that the system has to fly, right? The UAV must actually fly, right? And now one of the considerations that goes into defining those requirements is this scenario, right? And so it's not something that we would normally expect, because it's a very, very detailed part of systems engineering, is looking at different operational scenarios. But this is one that I think you should pursue, right? Is, do you have enough power to, I guess, maintain flight in very, very harsh conditions?
We have this term called a showstopper, and if you don't cover some of the little points at the initial stages, and you get to the big stage, further down, you spend a lot of money and you hit a showstopper. That can make life very miserable for an engineer, however. So sometimes the little details you keep in your back pocket, you think about them as you're developing your thought processes, so that when you get to spend money, you have a high degree of confidence that what you're contemplating will actually work. And so you might say, well, with that scenario that I just described, we need a bigger engine. The trouble is the aeroplane can't provide enough lift to carry it, so all of a sudden you're back to the drawing board.
Have you ever seen those? This is a good point that I'm sure you've had lots of experience with, but have you seen these plots of unrecoverable cost against identification of errors at certain points in the project, in the design phase? Conceptual design phase, cost is, let's say, 1, right? Preliminary design phase, cost is 10. Critical design phase, if you find an error, the cost would be either 100 or 1,000, right? And it goes up exponentially.
So you want to fix it.
Well, you want to identify the gaps early, and so again, another course specific thing that Mike will be able to agree on based on our observations from all the teams is that the biggest lesson that you need to get from this course is that you have to have all the information that you need to solve the right problem available, okay? And the only way you can do that is through very, very thorough interaction with the client early on, all right? And so that's what this is all about. This is what you're doing. You're finding this out, okay? And so I just want to make sure you all understand this, is that if you now go and do a final design, and then let's say you go and launch this thing, and then, we never considered that. We never considered the risk that this thing might have, fall out of the sky when it turns around because of the potentially harsh conditions that it's flying in. That's just one example.
I'll give you a real live example that you will be able to relate to, maybe, and that is the development of the 787, the Dreamliner by Boeing.
Yeah.
And they spent squillions of dollars, and they had it all worked out, and the computers said the thing would fly, blah, blah, blah. Right, composite material held it up 5 years, but they overcome that problem and the thing flew. And then the batteries overheated. And you'd have to ask, how could this possibly have occurred after the thing's been sold? 10 of them have been sold or in operation around the world, and all of a sudden you have a problem with this. In the scheme of things, the batteries are nothing. But that's exactly what happened. And I'd venture to suggest that the engineers probably didn't want to do it that way in the first place, but were beaten over the head by bean counters. And the bean counters generally always win.
So for the people that don't know what a bean counter is, it's an accountant.
Who here controlled the budget for this project? You're all engineers?
There's no,
Yeah, it was a sandbox.
sandbox budget.
Yeah, okay. But in the real world, there'll be someone out there who thinks only in dollars, and they'll be dictating to you as engineers what you can and can't do. But it'll never fall on their heads when it fails. It'll fall on yours. But ultimately, what that oversight with the batteries cost Boeing was, as Lyle was saying, the exponential cost of that. If they'd solved the problem 5 years ago, it might have been $100,000. What it cost them in late deliveries, reputation, and all the rest of it could be counted in probably 6-7 figures. Definitely seven figures. Millions of dollars. Right. So as you go through your careers as engineers, keep a very close eye on what the bean counters are trying to make you do.
But also just make sure that you are thinking holistically about everything every risk. This is why we drive risk so hard, right? Is that all the time when you're designing, you're continuously performing risk management, right? You're going, oh, what if this? This is called, looking at the operational requirements, right? And the scenarios, and basically thinking about all the things that could go wrong. And this is why pessimists tend to be quite good at this, because they always think of the really negative outcomes.
Yeah. But
But that's really useful. Okay, so that's just an interesting point, Michael.
I was going to say, sometimes you'll find you have the opportunity to overcome the encounters by.
So we have I'm not sure if any of you guys are particularly interested, but there is a lecture at 4, which means we have to get out at some point. Well, I need to leave, I think, because I'll be going to it. Did you have any other questions before I talk to them about the actual presentation style? Or did you have any comments on that?
No.
Okay,
I
so
think they're on the right track.
that's good. What I would like you to do is to summarise the concept that you have selected, that you are advising to go forward with, and write that out in some way so that Jeff can review it at his leisure. And basically, spending a bit more time thinking about it is always good. If you formalise that and send it over, that'll be great. This is just going to be a summary. Like, you're going to use a lithium polymer battery, and then justify it, right? And I'm sure you've written all that material already. Okay, send it over. That'll be great.
I do actually have a summary to give you.
Oh, wow, that's
Doesn't have the recommendations in here.
summarise the
This is a
recommendation.
summary of what we've.
Does it have any of the technical data that you talked about in the slides?
Yeah. So your slides, your charts were very sparse as far as information was concerned, which is not necessarily a bad thing. I think because the audience is very aware and very knowledgeable in the field, right? So you didn't need to run through anything. But yeah, so any documentation like that would be great to send through. So send it over.
As a matter of interest, how much do those batteries weigh?
Colin.
Oh.
Did you have batteries?
So what's the?
Well, I'm trying to figure out how big it is for a start.
It's the weight of a lithium polymer battery.
They're not heavy, but you do need quite a large battery to get the voltage that you want.
Yeah.
They're not-
Yeah. And what voltage is that? What volts?
Based on the research in the battery, the voltage is around 12 to 30 volt between. You can choose 12 volts.
Like there's different cells. Like one cell is 2.7 volt to 4V2. So if you can put three in series, so you got 12.4. Like you can stack seriously together. Like
And
one cell
delivering what sort of current?
current is depends on the capacitor. It can small can be 800 milliampere per hour up to 7,700 milliampere per hour.
Sorry, how many amp hours?
7,000 up to 7,000.
7,700.
Do you realise how much power is required to drive one of these things?
Oh,
Yes.
they do,
Yeah.
Yes, the power if we convert from the conventional engine is around 0.24 around 24 cc for the engine, the conventional fuel engines. So it's fuel engines.
Yes.
Yes, so it's like if you convert to an electrical engine, it's around 350 watts. So we need this much of the power.
Yeah, you need a lot of current.
You need a lot of current.
Yeah.
Yes.
So it sounds like if you got that many lithium polymer batteries on it, then I guess if that falls out of the sky, you're still in trouble. So you're still gonna have some sparks. That's interesting.
Yeah, the fuel, I don't know much about the fuel cells, but that's why we're so hooked on fossil fuels like petrol and things, because there's so much energy packed into a small space. Maybe worth looking at, in the scheme of things, if 3 or 4 litres of petrol fell into the middle of a fire front, what difference is
Oh, it's
it
only
really
if
gonna
you were
make?
going to engage from the front. If you started a fire in front of the fire front, that would be the risk.
Yeah.
But if your engagement, if your operation concept is to fly behind where it's already burnt, then you get it.
I think that would be.
So yeah, maybe that's it.
One of the key aspects was that if you're using a fuel powered motor, you'd have to have an alternator to power all the electronics on
Yeah.
board, or a separate battery power system. So that's also one of the reasons why we chose a battery or fuel cell approach.
I don't think there's
because-
anything wrong with having both. Your propulsion system is based on, well, the model aircraft don't use petrol, they use,
What?
It's constant.
It's a constant
supply of torque all the way up.
oh, right, yeah. But you have one of these, but much smaller driving the electronics, because the electronics is probably going to consume, well,
Yeah, but
Well-
so
watts,
thinking about onboard system, if you just have, so if you go to a fuel, so I have experience with the fuel UAV, and there's a whole bunch of other considerations you have to make. So if you went down that path, you would have to look at fuel tanks, which are going to be packed full of fuel, right? Then you're going to have this slosh protection, so that when you do this, all the fuel goes whoop, and then suddenly you have no stability. So there's a whole lot of really difficult challenges associated with that. But I'm confident in my own research that the battery for 30 minutes flight time with they'll be perfect, because the technology, everything's moving to the lithium polymer.
We're talking about SPs and stuff. You can get these people sort of control planes and absolute rockets.
Yes.
Electrical cars.
I think that would be something that you need to look at now for for the final design that you're going towards, is looking at doing a technology interested as well, right? So never be afraid to send an email with, hey, check this out. Okay, that's actually a point that I don't know if you want to comment on it, but you guys left the client in the dark and didn't communicate with him a lot in the first 5 weeks of the project.
Yeah.
This is a really bad habit to get into, and it's something that a lot of people make, right? This mistake. Okay, so it happens, and it's something you have to learn from. But I'm driving it here now. You cannot leave them in the dark during the most important phase of the project. You know this cost against error thing? That's why, right? And ordinarily in the real world, if you work for an engineering firm, then you'll be meeting with the client a number of times like this, right? You'll have these things, you have conceptual design reviews and requirements analysis reviews where you make sure that you're solving the right problem.
Yeah.
Okay? But you guys, I just want you to recognize that yes, you made a mistake, right? You didn't go. If no one's to blame, it's just something that went wrong, so long as you understand that you can never allow that to happen again.
see, related to that is the fact that you'll often have clients that think they know what they want, but they don't really know what they want. And it's better to identify that scenario sooner rather than later. Because I have it right now with what I do. What I'm selling stuff to, the customers have no idea what it really is that they want.
Yeah.
And when they get it, they don't really fully understand what it is that they got.
No, they just want the best.
It's not like a,
Yeah, and they want to pay the minimal amount for it.
This has bitten some groups before where they've gotten halfway through the project and they get it all the way out to the 3 ideas design and it's like, well, we don't want him. You know?
Well, that has happened, yeah. It's kind of funny actually, but you know. Or the other, here's an example. The other UAV team, right, the Fast Solar, their client has said that I want your solution to be a UAV, right? And this is a visual inspection system. And guess what? One of what we call the mission statement of that project is to detect hairline cracks in a steel structure using a UAV, like a hovercraft. And impossible. It's absolutely impossible, right? You can't do that because you can't get enough stability, you can't get a fast enough shut time, you can't do a whole lot of things, right? And you know, this solution is estimated to cost $25,000 per unit, right, at the moment. And then, you know, I said, look, do you need to really have a UAV? He said he wants one, but he doesn't know what he's talking about. He just thinks it's a cool idea. And then everyone was like, well, what if we had like cameras mounted on the ground that had telephoto zoom, right? Telephoto lenses mounted on it and then looked at
Looking at what?
At the tower, at a structure. And
looking
Because they're
for
looking
what?
for hairline
for looking
cracks
for
and
hairline
stuff.
cracks in steel and in piping and stuff like that. And I was like, okay. And so they worked that out, and it would be about $1,500. And it outperforms the UAV solution in every possible way. And they determined that using the House of Quality, right? And so that's going to be really interesting tomorrow when they're presenting on Monday to their client when they say, look, sorry man, but you're an idiot. Here, use this. Of course, you'd be a bit more tactful when you present that, but you say, look, this is cheaper, it's better, and all that. But this is the thing. The client ordinarily would be made aware of this in an internal CDR, right? And then he would be able to review, talk about it with his company, all that kind of stuff. Yeah. But it's interesting how the client would say, oh, I want this. And usually they want it because, well, if they knew what they really wanted and how to do it, they would do it themselves probably. Okay? So that's something to keep in mind. In that case, you're the experts. So
Yeah, and then you'll get them also saying, well, we want this, but you're going to have to do it that way. The most common, it's a little hobby horse of mine, but one of the most common directions I've ever had in my time is what operating system to use. We want these features, but you're going to have to use Windows.
yeah.
Sorry, ain't going to work.
They don't care, they don't matter. I'm going to send you guys a video about how difficult it is being an expert in AI. You've seen this one?
Is it the one with the red line?
Yes.
Yeah.
I want you to draw 5 perpendicular lines.
7.
7. All perpendicular to each other.
And they've got to be red, but you've got to use a green.
You got to use green ink. Anyway, it's a perfect summary of how shit it is to be an engineer. All right, very, very, very clear. That was very impressive. Okay, so as far as the actual delivery of the presentation is concerned, I thought it was very good. I thought it was very clear. I thought, despite having palm cards, which I normally don't like seeing, you know, you were quite good with them. You weren't glued to them. A few people were a little bit. It's understandably nervous. Okay, that's completely understandable. You don't get marked down for it, but the way to get over nerves is to just know your shit. Just know it inside out. Did you pick up on that?
Yeah.
And even I get very nervous if I'm not 100% and super confident on the material. I get very nervous, and you start fluttering in your speech and you shake basically, and you also take long times between sentences to try and compose yourself. Okay, and that's a good point though. Instead of saying right, you have to. One good thing is when you're talking to people, if you're in the habit of doing ums and ahs, think about it very, very carefully, and you have to be aware when you're doing this, when you're saying and just try and force yourself to close your mouth and make no noise. Right? And so, Jaden, that was actually something that you did very, very rarely, but I picked up and I thought you might want to know about it because a lot of the time when you're speaking publicly and you say you don't know about it. It's something that you're completely oblivious about. I did it 3 times.
But then it's gone to the microphone. It's like, oh.
yeah, you get massive feedback and whatever. Visual aids were simple. You didn't have a lot of technical information. Typically what I would like to see is an actual handout given to the client, right, that has a summary of all the technical specs that you're dealing with. That's just something to keep note of. That's more of a content thing. So I noticed you provided food and water. Very good. Okay. Sometimes it's very unlikely the client's actually going to eat it. You're not going to have any of that stuff, are you? Maybe.
That was there.
Maybe you're gonna have some.
Fine.
Right? It's not about them eating it. Don't feel bad if they don't touch it. It's the fact that it's there, right? It's called extending courtesy, and that's very, very good. And you know, it doesn't matter how many times I told my teams last year, they didn't do it because they didn't want to.
Oh, wait.
No, that was first semester. Yeah, Ferrero Rocher. That's a good way to.
How the budget line.
Yeah, is that in the budget? I don't know. Do you have anything, Dad?
Yeah, I was mostly sort of, I'm a very visual person. I wouldn't mind to see some pictures of your ideas, concepts. You said you were John looking out for certain technology out there, UAVs and all that sort of stuff. I wouldn't mind seeing some pictures of those rather than the generic fixed wing quadcopter type stuff. It's just to give a good idea of specifically what you're looking at.
Yeah.
Rather than just a generic thing with wings and a motor. So that's just the main thing I'm looking for. The other thing is like you're talking. It's not. Lyle said it's not a bad thing if you don't have technical details in the slides, but sometimes it's nice to have a few quick sort of basic things. You know, what sort of power do you need? How fast is it? How big is the wingspan? You know?
Yeah. So concepts. So have you heard of a thing called an operations concept? Okay, so here's what an operations concept is. Thing launches, it's got a payload on it that can detect fire, so it flies up, and so it's in stages of what it's doing, like it's actually operations, right? Goes up, and then when it's actually performing its mission, there's some concept behind that, right? And so what I was describing before, you've got this UAV and it's got a camera pointing down to the left or to the right. That would be its operational concept, okay? To detect, to satisfy the mission requirement, right, which is to find hotspots or fires, this is what this concept is going to do in operation, right? And sometimes it's useful to actually draw that out as a little picture. So what you could have is that little picture of that. You could have a picture of the grass on fire, and then you could have the field of view drawn in of the camera, and then you could have GPS up here, and then you could have